Hello, this is a quick lesson about algebraic bookkeeping, which just means how can you organize your algebraic process so that it doesn't overwhelm you with its own complexity. So what we had done in class was we were deriving a curve that consists of all of the points xy such that the distance from xy to a point at -3, 0, plus the distance from xy to a point at 3, 0, so those two distances added together, is always 8. So I've drawn a little sketch here. If d1 is this distance and d2 is that distance, I want all of the points so that d1 plus d2 equals 8. Okay, so let's do it the wrong way first. Let's do it without doing any bookkeeping techniques and kind of watch how terrible it is. So d1 is going to become like a distance formula. So I'll say x minus 3 squared plus y minus 0 squared is just y squared. Okay, so now I've got root here, so this is going to be x minus opposite 3 is x plus 3, and this is y squared equals 8. Okay, I want to get rid of these square roots, so I could square both sides, and this is going to turn terrible immediately. Well, let's move one of the roots to the other side. I'm not going to have no bookkeeping techniques. So if I move one of the square roots to the other side, I'll have this 8 minus the square root of x plus 3 squared plus y squared. And now I can square both sides because strategically what I'm trying to do is get rid of the square roots so I can start combining things. So here, this becomes x minus 3 squared plus y squared because the root is undone. Here I have to expand this, so this is going to be like 8 times 8 is 64, minus 8 of the square roots, minus another 8 of the square roots is 16 of those square roots. And then the square root times itself is going to be x plus 3 squared plus y squared. Okay, great. Again, strategically, I need to get rid of the square root inside this term. So let's move everything over to this side. So now I've got x minus 3 squared, and then I'll subtract x plus 3 squared, and then, oh, I'm noticing y squared and y squared are canceling. That's nice. So I can subtract y squared from both sides. And now I'll subtract the 64, and then that's negative 16, and now I've got square root all this stuff. And maybe you wanted to divide by 16 before you square, so let's do that. So here's divided by negative 16. So now I can square both sides, and on the right it's going to go very well. This just looks like that. On the left, now you're maybe feeling a little less saucy because I have 3 terms that I have to square. So it's not like a plus b squared, it's like a plus b plus c squared. And this is going to be like a lot of algebraic work to kind of work out, and then you got to divide everything by the 16. And so now I've reached the point where I'm feeling like, I'd rather not do this. So let's go back and try and do it a better way. Okay, so the first bookkeeping technique is don't mess with big ugly expressions until you have to. So yes, it's true that d1 is this square root and d2 is that square root. Uh-oh, all the lights went off. Okay, I'm back. But there's no reason to move them all around like this. Like this equation looks very simple. This equation looks very complicated. They're the same equation. So if you're going to do algebra, wouldn't you rather do algebra with the one that looks simple? So let's do that. What I did last time was I moved a square root to the other side and squared it. So let's do that same thing, except let's just keep d1 and d2. So I'll say d1 equals 8 minus d2. So I just subtracted d2. Now I can square both sides. So d1 squared, so now I can think what is d1 equal to. So d1 is the square root. When I square it, that'll give me x minus 3 squared plus y squared. d2, let's go ahead and expand this without actually substituting in the expression for d2. And rather than multiply out 8 times 8, I'm going to keep it as 8 squared, just because that might make it easier to cancel things later without a calculator. So minus 16 d2s, and now plus d2 squared. Okay, so now that I've got d2 squared, I can substitute in for d2 squared. So let's do that. So we've got 8 squared, 16d2, and then d2 squared is just going to be the x plus 3 squared plus y squared, and then this is x minus 3 squared plus y squared. Okay, so let's subtract out the y squared from both sides, and let's isolate d2 the same way we were trying to do before. So I'm going to subtract this x plus 3. So I've got x minus 3 squared, and I'm going to subtract x plus 3 squared, and I'll subtract the 8 squared as well. Then I'll have negative 16d2. Okay, but before trying to do anything, let's simplify this side, because the whole thing that led to the problem last time was I didn't try and simplify this at all, and so then I was trying to like square a whole bunch of crazy mess. So let's expand each of these. And you'll notice something else I'm doing is rather than starting at the left and working my way to the right, I'm sort of creating spaces for the expansions that I know are going to be there. That's a nice technique also. So when I expand this, I'll have x squared 6x 9. When I expand this, I'll have x squared plus 6x plus 9. And then on this side, I've got still the same thing. So now a nice thing's going to happen. I've got x squared minus x squared. So that makes 0. I've got 9 minus 9, so that makes 0. And now I've got negative 6x minus another 6x, so that's going to make negative 12x, and then this is minus 8 squared, and then that's negative 16d2. So see, it expanded to get ugly, but I'm still feeling calm because that doesn't look so bad. So let's keep going. I'll multiply everything by negative 1. To get rid of the negatives. I'm noticing that I could be simplifying this. So now actually in order to simplify it, let's rewrite it as 64. 16d2. So I can divide by, well maybe let's divide by 16 and see how everything simplifies. So if I divide by 16, that will be divided by 16 and this will be divided by 16. So 12 over 16 is just 3/4. 64 over 16 is just 4. So this is working out very nicely. And now we're in a good position to substitute back in D2, which was this, as I recall. So I know you can't see what I'm writing right now, but I'll show you in just a second. I'm substituting back in D2. There it is. Okay, so now we can square it and take it the rest of the way out. And when I said these are bookkeeping techniques, the bookkeeping techniques doesn't make this process shorter. It's still a long process, but it's a process that you can at least get through. Whereas before, it's a process where you keep going and then eventually you decide that you're going to stop. So let's square both sides. So now I've got 3/4 x plus 4 squared equals x plus 3 squared plus y squared. I'm going to want to combine all of the x bits, so let's do that. I'm going to subtract this and expand it at the same time. So this part expands as 9/16 x squared, and then when I multiply 3/4 and 4, that gives me just 3. And then when I do it again, that gives me another 3, so that's just 6x's. Plus 16. And then on this side, when I expand it, I'm getting x squared plus 6x plus 9. And so again, we can kind of see what cancels. So those don't cancel, but I got 6x minus 6x. So those subtract to become 0. 16 and 9 become, well, it's, okay, so 16 minus 9 becomes 7. 9/16 x squared minus x squared. So maybe that's worthy of just writing out that way. We can combine those in a second. Was this minus? No, this was plus because it was 16 minus 9. Okay. Equals y squared. So how are we going to combine these? You could think about it two ways. You could think about factoring out an x squared, or you could think about combining under the same denominator. So x squared is the same thing as 16 over 16x squared. So if I have 9/16 x squared minus 16/16 x squared, what's that? That's going to be negative 7/16 x squared. And so now let's move the x squared to the same side as the y squared. And so we've got 7 equals 7/16 x squared plus y squared. And we were able to get to the end. And this looks like an ellipse. And we know what the scale factor is. And everything's great. Okay, so kind of a lengthy process. But calculus requires that you do a lot of lengthy algebraic processes. So, wouldn't it be great to train yourself to make sure that you felt good being able to do that kind of thing? Maybe it wouldn't feel good in the training, but boy, will it feel good afterwards, which is true of all types of training. Okay, I hope this helps you. Good luck.